In today's class, we want to examine geometrical ratios. Under geometrical ratio, we have the aspects such as similarity. We have where we can apply angle bisector theorems and some other aspects. Basically, we'll restrict this geometrical ratio in a class to similarity, as this is mainly what external exams, most of them, whether IGCSE or you talk about SAT, ACT, NECO, and WASC. These are the aspects they center on, including UTME. So we want to talk about similarity. And the concept similarity simply implies that imagine a boy and his father. Someone look at the boy and say, wow, you look exactly like your father. Exactly like your father. So if they said they look exactly, if they said this boy looks exactly as his father, it doesn't imply that they are congruent, that is, they are of equal size. No. It means that the ratio of their corresponding parts is constant. For example, if you say the length of their hands, length of hand of the son over length of hand of the father, the ratio it will give you is equal to length of maybe length of the head. For example, length of head of the son over length of head of the father equals to, it could be maybe length of stomach or leg of the son over length of the leg of the father, and so on. So any part you pick on the son, the length is equal, you take it as a ratio of the one of the father. The ratio it will give you will be equal to if you measure any part on the son as a ratio of that of the father. But one thing is that this ratio, we get it as whatever you pick on the son, that's what you pick on the father. And since the son we first talk about, in every occasion it is son first. But suppose you don't want it like that, if you first mention father, maybe you say hand of the father, it will be over hand of the son, and so on, equals to head of the father over head of the son, and like that. So that's what the concept similarity is talking about. It's talking about that if you have, and how do we relate this to triangle? If you have two triangles, I told us the concepts, when we say two figures are similar in mathematics, it doesn't mean they are of equal height. They are of equal size. No, for example, look at this. We have triangle XYZ and we have triangle ABC. So these two triangles, suppose the angle of this one is 50, the angle of this one is 80. Or let me use 70 here. So if this one is a 60 and this one is a 70, and they're asking you, do we know that the two triangles are similar? Two triangles are similar if they are equiangular. And the term equiangular means their corresponding angles are equal. If two triangles are equiangular, we say they are similar. How do we know whether they are equiangular? All their corresponding angles must be the same. What's the third angle in this triangle, XYZ? The third angle is 50 plus 70, which will give us 120. Subtract from 180. 120 from 180 will give us 60 degrees here. And for this one, 60 plus 70, that will give us 130. Subtract 130 from 180, we'll get 50 here. So it is now glaring, obvious to us that the two triangles have their corresponding angles equal. If you look at triangle, that means we can now say we use the angle to arrange the letters. So in the triangle XYZ, X, or let me put it this way. Look at, in the triangle XYZ, angle X equals to 50, and that is equals to angle C, equals to angle C. Angle Y, which is a 60, equals to angle B in the second one. And angle Z, which is 70 here, Z, 70 is same thing as angle A in the second triangle. So we can now use this lettering now in this order, X, Y, Z. We can now say triangle X, Y, Z is similar to triangle. The way you label, the way you arrange these letters, just follow that arrangement like that. So you say triangle CBA. That means triangle XYZ is similar to triangle CBA. In this case, since it is like this, we can now follow what I said. The ratio of the size of these two triangles will be constant, will be the same. For example, let's pick, just like if you see this one, this triangle XYZ as sun, like that analogy I gave in the first place, when I started the explanation of this concept. Triangle XYZ is similar to triangle CBA. This XYZ, we see it as the son, and this CBA, we see it as the father. So if I pick any part of this son, for example, let me say I pick XY on the son. What part of the father is corresponding to XY on the son? So the first two letters, it will be CB here. It will be over CB. Just like I say, the length of the leg of son over the length of leg of father equals to, if I pick another part of this triangle now, I have picked XY, I can pick another side, which is Y. Let me choose YZ this time, YZ. So which side is corresponding to YZ? On this one, it will be BA. And lastly, Z side I am here to pick on this triangle. I have picked XY. I have also picked YZ, remaining XZ. Side XZ, the ratio of XZ to this one will now be CA, sorry, to be CA. So that means whatever ratio or fraction you get here will be the same as this, will be the same as this. That's what the concept similarity is talking about. Let's quickly go into this example one and see how it unfolds. This one, we have to find YZ first. So we go to A. To find YZ, you must be able to show that there are two triangles in this diagram, XPY and XYZ. So we want to show that the two of them are similar. And for you to justify that, you need to establish that they have their corresponding angles equal. So first of all, if you look at the first triangle, this XPY, XPQ, and the second one, the bigger one, which is XYZ. You can see that angle at P, because this side, PQ is said to be parallel to YZ. The angle here is corresponding to the angle here. That means the angle at P here equals to the angle at Y here. And also, angle at Q is corresponding to angle at Z. So the one here equals to the one here, meaning that this one equals to the one here. And once you are able to establish that two angles are equal for two triangles, the third angle too automatically will be equal, because if I add the two together and subtract from 180, what I will get would be the same as when I had the two together here too. Since it is the same thing I'm adding together and subtracting from the same total, so I will always get the same thing. So that means the angle at X here equals to the angle here. Another way of saying it is that the two triangles converge at this point X. That means they share this point X, and the angle there is common for them. That's their common angle. So that means this angle X is the same for them. And from there, we now want to establish. Look at the similarity of, let's write the first one. If I say triangle XPQ, triangle XPQ is not equals to, don't use equals to, because the two of them are not congruent. They are just similar. And look at the son and the father I drew for us at the beginning of the class. You can see that they are not of equal size. They are not equal. It's just that they look alike, and we call it, that means they are mathematically similar. Hence, the ratio of two similar objects, the ratio of their corresponding size is constant, is the same. So in this case, it's the ratio that is, so triangle XPQ is similar to triangle, in that case, X here, X here. In the second one, this P is corresponding to this P is corresponding to this Y. And this Q here, which is is corresponding to Z. You can see their angle double marked. So we have Z. From here now, you can now say this is son, this is father. So if I pick XP on the son, it will be over XY on the father, which is, if I choose PQ on the son, I choose YZ on the father. And if I choose XQ on the son, I choose XZ on the father. XZ. So once you're able to establish or generate this ratio, go back to the diagram and substitute the available values or the given values. So on this now, we have XP. Are we giving XP? Yes, that is 2 over, what about XY? Are we giving XY? X to Y is 2 plus 3, which is 5. Equals, so are we giving PQ? PQ, that is 6 over YZ. That is what we have to find. YZ, which is equals to, are we giving XQ? XQ is not known. SQ not giving, over XZ. Are we giving XZ? Let's check. It's not giving either. XZ. So when you have this, you can clearly see that you know the whole of this ratio and you want to find this one. So just choose these two and solve. Choose those two and solve. We have 2 over 5 equal to 6 over YZ. When you cross multiply, that should give you 2YZ equals to 5 times 6 will give us 30. And for you to find YZ now, we remove this coefficient. We divide these coefficients, you divide both sides by 2. So that is going to give you YZ equals to 30 over 2, and YZ becomes 15. That is 15 centimeter, and that's what we have to find there. YZ is 15 centimeter. So we quickly go and find this one. For us to find the area of this trapezium, we can see the trapezium here, PQ, ZY. The area of this trapezium, there's no way you can find this trapezium directly because you are not giving any angle and you don't know the perpendicular height. Suppose you are giving any angle now, you may think of, let me work my way out of it. Let me try and work out the height. But you are not giving information to find the height. We still follow this similarity to do that. But imagine that you know the area of the two triangles. We are giving the area of XPQ to be 24. XPQ, the area of this smaller triangle, to be 24, and we can use that to generate the area of the bigger triangle. Once we know the area of the two triangles, if you subtract this smaller triangle, if you detach this smaller triangle from the whole diagram, you are left with this trapezium. In other words, if you subtract the area of the smaller triangle from the area of the whole triangle, the larger triangle, it will leave you with area of this trapezium, and that's our target now. Let's see how it also goes. Don't forget, one particular complete ratio we already have, we'll use it, is this one. The ratio of XP to XY, we have it already. We use it in our next working now. And of course, we already have this one too now. 6 over our YZ is 15, and 6 over 15, you know, if you have 6 over 15, 3 in 6, 2, 3 in 15, 5. You see that it's the same thing as this. That is why we say the ratio of their corresponding sides will be the same. That means what we have here, which is 6 over 15, the same thing as 2 over 5. If you have enough information to find the ratio here too, it will still be 2 over 5 eventually. So we'll use that 2 over 5 as our scale factor for the two triangles. So in B parts, in B, we're given that the area of triangle XPQ ratio area of triangle XY. Let me choose a XZY. Okay, the two triangles, the smaller triangle here and the whole triangle, which is the bigger triangle. The ratio of their area equals to, since they are two similar triangles, will be equals to what's pick two particular corresponding sides for each of them. If I pick this side on this one, XP, if you check the previous example, this XP corresponds to on this for this smaller triangle because it faces this angle here. XP faces this angle, and in the larger triangle, the side that faces this angle Z here is the entire XY. That means the same thing as XP over XY. But one thing is that since this one is area, for example, you know area is in centimeter square and side is in centimeter. So to confirm the two on the same unit, so unless this one, if centimeter multiplies centimeter, it becomes centimeter square. Anytime you are taking ratio in similarity and you are comparing ratio of area, so if you have anything like ratio of side, to confirm them, you must square each of them. If it is ratio of volume and you have ratio of side, for you to equate them, you must take cube on each of them. So they are on the same unit now. We now substitute, what's the area of triangle XPQ? That's 24. 24 over area of the second one, we don't know it. That is XZY. That's triangle XZY equals to XP is 2. That is 2 squared over XY is 5. That is 5 squared. So we can now cross multiply. 25 will multiply 24. That is 24 times 25 equals to 2 squared will multiply, that is 4, multiply triangle XZY. So from here, we divide both sides by 4. So that this 4 will go. We now have area of triangle XZY to be equals to, here, 4 here 1, 4 in 24, 6. So if you do 6 times 25, you should get 150. That means the area of the whole triangle is 150. Therefore, to find the area of the trapezium, area of trapezium that is a PQ ZY equals to the area of the whole triangle 150 minus the area of the smaller triangle 24. And that should give us 126 centimeters squared. So that's the end of this example 1.